Good day. We are going to solve the following conservation of energy problems for your review. Let's start with the first problem. Just before striking the ground, a 2 kilogram mass has 400 joules of kinetic energy. If friction can be ignored, from what height was it dropped? The answer is 20.4 meters, not 20.0. Okay, so this is my solution. I apologize if I just wrote it by hand, but I understand that this is a free fall type problem which can be solved using conservation of energy. First, the given is the mass is 2 kilograms and it has a final kinetic energy of 400 joules just before it hits the ground. Its initial velocity is 0 because it was dropped, and its initial kinetic energy as a consequence is 0 because initial kinetic energy is related to initial velocity. So initial height is 0, so we are setting up our Cartesian plane so that the initial location of the mass is at above the 0, where we set our 0 to be the final height. So this is arbitrary. So we set our 0 to be the ground, right? So that's and that is the final location of our mass. Our initial height is a few meters above the ground. This is just arbitrary. You can choose wherever you want your height 0 to be, but in this case, I decided to put HF equals 0 at the ground. And our change in kinetic energy is 400 joules because kinetic energy final minus kinetic energy initial is 0. And our UGF, this is U, this is our gravitational potential energy final is 0 because I set 0 to be at the ground. So just before striking the ground, of course, since the height is 0 for the mass, its potential energy at that location is 0. And of course, UG initial, we don't know what it is yet, but we can find that if we know HI. So if we model this problem to be so that our system is the mass and the earth, the mass and the earth, we have a situation where the system is isolated. There are no external forces acting on our system consisting of just the mass and the earth. And because of that, we can use this formula for which comes from delta, which comes from some like change in E total, I think. So that equals 0. Since our system is isolated, our total energy does not change. So there is no change in our total energy within the system. So any change in kinetic energy plus any change in potential energy is equal to 0, right? There is conservation. Rearranging, delta K is equal to negative delta UG. And delta UG is, of course, UG final minus UG initial. So, and we know that UG final is 0. So we are left with delta K is equal to UG initial. Rearranging, we have MGHI from UG initial is equal to delta KE. And HI is equal to delta KE over MG. Substituting the known values, we find that HI is 20.4 meters. Okay, no? So this problem, usually for free fall problems with no air resistance, we can model the situation as an isolated system and use this formula. So, next question. A 0.5 kilogram ball falls past a window that is 1.5 meters in vertical length. A, how much did the kinetic energy of the ball increase as it fell past the window? And letter B, if its speed was 3 meters per second at the top of the window, what was its speed at the bottom? This is another free fall problem. And as I mentioned earlier, we can model this so that the system is the ball and the earth. And if we have that system, we can say now that the system is isolated. And so we can use the conservation of energy equation. But the given here is that the mass of the ball is 0.5 kilograms. The initial height is 0, and the final height is negative 1.5 meters. So in this case, I set up my Cartesian plane or my y-axis so that y equals 0 is at the initial location, hi, and, sorry, it's not straight. Y final is negative 1.5. Again, this is arbitrary. It is your choice. I could just have easily placed y equals 0 at the location of the final height. But this time I chose this method. So again, we can use delta k plus delta ug equals 0, where since our system is isolated, so any changes in kinetic energy plus any changes in potential energy within the system is equal to 0. And there are equal to 0 because there are no agent, no energy transfer happening. No energy transfer happening because our system is isolated. Again, rearranging, and we have delta k is negative mgh final minus mgh initial. But in this case, our mgh initial is 0, so we have delta k is negative mgh final. So substituting known values, we have delta k is 7.35 joules. So the change in kinetic energy is 7.35 joules. In other words, to answer letter A, the ball's kinetic energy increased by 7.35 joules. So for letter B, we are asked to find the final speed of the ball. Now we utilize the delta K is 7.35 joules, right? So since we already got this from letter A, we can just use this. But delta K is just the change in kinetic energy, so that's K final minus K initial is equal to 7.35 joules. And just expanding the formula for kinetic energy, we have 1/2 mdf squared minus 1/2 mvi squared is 7.35 joules. Rearranging, and now we find, to isolate V final, we find that the final velocity is 6.196 meters per second or 6.2 meters per second. So let's move on. Oh, I did not know this. All right, anyway. So let's just look at this one by one. The coefficient of kinetic friction between a 900 kilogram car and the pavement is 0.8. If the car is moving at 25 meters per second along level pavement where it begins to skid to a stop, how far will it go before stopping? So here in this pictorial representation, I represented the car as a box. The car, I assume, moved to the right, and there is a friction force acting on the car, slowing it down, giving it constant acceleration. Actually, that slows it down. So first, let's look at the system schema. So there are three main actors in our problem: the car, the floor, and the earth. And for this particular problem, I chose my system to be just the car. So clearly, if you look at our system schema, there are external forces acting on the car. The gravitational force, the friction force, and the normal force. Therefore, we can model the car as a non-isolated system with the work done by friction acting as an energy transfer mechanism acting on the system. So among these three forces, if you now look at the free body diagram, we have the normal force, the friction force, and the gravitational force. The normal force and the gravitational force actually do no work on the car. So they do not do work on the car because the normal force and the gravitational force, they don't do any work on the car because they are perpendicular to the displacement of the car. And if you remember your work formula, it involves cosine theta, right? Where theta is the angle between the force and the displacement. So for theta, in this case, you have to use 90 and cosine 90 is 0. So normal force and gravitational force do zero work on the car, but it is the friction force that does work on the car. So the work done by friction is our energy transfer mechanism. So for this non-isolated system. But I have not told you this, but there is a formula for calculating the kinetic friction or the friction that occurs between two interacting objects sliding past each other as they are moving. So as the car is moving, it slides across the floor, and that motion, there is friction between the car and the wheels of the floor. And that friction is known as the kinetic friction because there is motion involved. And the formula for getting kinetic friction is mu k F sub n, where mu k here is the coefficient of kinetic friction. It's a unitless number. In this case, in the problem, it is 0.8. And multiply that by the normal force. The normal force, we can get that from Newton's second law. The summation of forces along y is equal to 0 because the car is equilibrium along y. And there are two forces along y, the normal force j hat and the gravitational force negative j hat. So normal force minus gravitational force is equal to 0. Therefore, we can say that the normal force is equal to the gravitational force in this case. So normal force is equal to mg in this case. So we just substitute that here. So therefore, we have our equation for the kinetic friction acting on the car. It's mu k mg, where m is mass and g is 9.8 meters per second squared. We need this expression, FKF UKMG, because we are to calculate the work done by the friction. And so we have this formula here. The change in energy of the system is equal to the sum of all energy transfers acting on the system. And in this case, the system is non-isolated. So in our case, there is only one energy transfer, and that is via the work done by friction. So the work done by friction is the force, the displacement, and cosine 180 because friction is to the left and the displacement is to the right. So this, and so here on the left side, the total energy change of the system, delta UG is actually 0 because if you remember, UG is gravitational potential energy, something to do with the position of the object. And as you can see, the car did not change its height. The change, there is no change in height of the car because it is only moving horizontally. Therefore, there's no change in the gravitational potential energy of the car. So we are left with kf minus ki is 0. And kf, of course, is 1/2 mvf squared. Ki is 1/2 mvi squared. And cosine 180 is -1. So that's the negative sign appears here. And of course, FKF, or the kinetic friction force, is UKMG. And we are looking for D. Here, we just multiplied both sides by 2 to remove the 1/2. Here, we started isolating D because the problem asks for how far the car will go before stopping. So final velocity, in that case, is 0 because the car stopped. Substituting values will give us D is equal to 39.86 meters or 40 meters. So we have another problem. Consider a simple pendulum shown in the figure. A, if it is released from point A, what will be the speed of the ball as it passes through point C? So if it starts here, it released, so initial velocity is 0. What will be the velocity at C? Yeah, final velocity at C. So this is very hard to solve other than using energy consideration. So let's read what I wrote here. If we assume that the pendulum is ideal pendulum, and that the tension, if we assume that the pendulum is ideal and that the tension force is always acting perpendicular to the displacement, then we can say that the work done by tension is 0. So in this case, for example, the displacement is going that way, and the tension is, of course, going up that way along the rope. You can assume that for all parts of the pendulum swing, the displacement is always perpendicular to that tension force. So we can say that the tension does no work on our system if we define our system to be the pendulum bob and the earth in this illustration right here. Yes, the tension is an external force, but it does not provide any energy transfer to our system in the form of work because the work done by tension on the system is 0. So given here, HI is 0.75 meters. So now we assume that our Cartesian plane, our 0 is where point C is. So our 0 is where point C is, and our therefore location of point A is 0.75 meters. Okay, and our final height, therefore, if we we are asking what the velocity of the ball is at point C, so that's where our final height is. Our final height is 0. Note that we arbitrarily set h equals 0 at the location of C. Initial velocity is 0 at point A, and final velocity, that's what we are looking for. And therefore, again, we can use this formula. But since the work done by tension again is 0 on our system, therefore we can set that equal to 0. And delta K, of course, K final minus K initial, and delta UG is UG final minus UG initial. From here, we just isolate KF, and in particular, we isolate VF, and everything else is given. No? UG final is kinetic initial is 0 because initially the pendulum is not moving. And final gravitational potential energy is 0 because at point C, H equals 0, so MGH becomes 0. But MGHI is not 0 because HI is at 0.75 meters. We isolate VF when we find that the answer is at point C, the velocity is 3.83 meters. For letter B, what is the ball speed at point B? So in this case, I choose I choose my initial to still be at point A and our final to be now at point B. Just want to find what the height is of point B, where it maps in the y-axis. So I realize I need to utilize this right triangle and use the Pythagorean theorem or the law of sines and cosines. Not the law, but the trigonometric ratios. I know here that this is just the length. The hypotenuse is just the length of the rope. So that's still 0.75 meters. And I can solve for y. This is not the height yet, but this does not show what the height is above 0. But y using cosine 37 is 0.599. And so where it maps in the y-axis is that 0.75 minus 0.599, so 0.15. So that height above the 0 is 0.15 meters, height of B. And as I mentioned, I chose initial at A and final at B. Well, you can also choose your initial at C and your final at D, and you get the same answer. So, and I use this again because same as before, where this may not be an isolated system in the strictest sense, but since the work done by tension is 0, it looks like an isolated system. And isolating VF again, we find, in this case, UGF and UGI, they are not 0, but kinetic energy initial is still 0 at point A. But we can solve for 3.4. We'll find that VF is 3.4 meters per second. Finally, the last problem, a child whose weight is 267 newtons slides down a 6.1 meter playground slide that makes an angle of 20 degrees with the horizontal. The coefficient of kinetic friction between slide and child is 0.1. So how much energy is transferred to thermal energy? Letter B, if you start at the top with a speed of 0.457 meters per second, what is your speed at the bottom? So letter A, how much energy is transferred to thermal energy? This is equal to the work done by friction, no? Or the friction force multiplied by the displacement. So the energy change, no? Thermal energy. Because friction, that's what friction does, converts into heat. It takes some of that energy away and turns it to heat. But let's draw the problem. Here we have our child, represented by a box, yellow box. And these are the 3 forces acting on the child. The normal force, which is always perpendicular to the... Okay, so if we tilt the axis like we normally do when we deal with like inclined planes, right? We will find now that the normal force is now vertically upward. The gravitational force is angled at 20 degrees. And the kinetic friction force is pointing westward, exactly to the left. Now we have to break down the gravitational force into its components, Fgx and Fgy. And for letter A, how much energy is transferred to thermal energy? The answer to that is we need to solve for the kinetic friction force and then multiply it by the displacement of the our child, or we represent as a block. And if you remember from the previous problem, the formula for kinetic friction force is UK, coefficient of kinetic friction, times the normal force. In this case, if you look closely, since looking at the free body diagram, the normal force is equal to the y component of the gravitational force, because all the y forces are in equilibrium. So that means that the normal force is equal to Fg cosine 20 degrees because it is the adjacent side for 20 degrees. So therefore the normal force is equal to mg cosine 20 degrees. Therefore, our kinetic friction force is equal to mu k mg cosine 20 degrees. And as I mentioned, the how much energy is transferred to thermal energy, it's the kinetic friction force multiplied by the displacement or right. And now we substitute values, we get 153 joules. So notice that the the change in thermal energy is equal to the work done by friction, but this case the positive version of that. Because if you think carefully, the work done by friction actually is negative because the direction is friction is opposite the displacement, right? Yes. So but in this case, we get the positive value of that 153 joules. Right. So for letter B, if the child starts at the top with a speed of 0.457 meters per second, that's initial velocity, which will help us solve for initial kinetic energy. What is her speed at the bottom? This is a case wherein if we treat the child as our only object in our system, we can treat this problem as an isolated system. And the change in energy of our system is equal to like one energy transfer, which is the work done by friction. We already solved for the change in thermal energy, and we acknowledge and recognize that the negative of that is the work done by friction. So 153 joules. So negative 153 joules is the work done by friction. Again, it's negative because the direction of friction is opposite that of motion or cosine 180. Okay, and kf minus ki plus cgf minus cgi. Right, just isolating final kinetic energy because we want to isolate the final velocity. All the masses are cancelled, except here, we divide 153 joules by the mass because when we divided both sides by m, so all the m's here, wala ng m, no m here, no m, no m. But since we divide everything by m, right, so 153 joules divided by m. And also, mass of the child is not actually given, but what is given is the weight of the child. But we know that weight is just mass times g. So therefore, mass is weight divided by g. That's why we have here, right here, 267 divided by 9.8 in place of the mass. Also here, initial height, which is right here, hi, that is just the opposite side of this right triangle, which is the inclined plane. So, and the hypotenuse, of course, of this inclined plane is 6.1. As mentioned in the problem, it's a 6.1 meter playground slide. So therefore, to get hi, we just get sine 6.1 times sine 20. That's where this comes from. Therefore, substituting all known values, we have final answer of the velocity of the child at the bottom is 5.47 meters per second squared. Thank you, and I hope you learned something